Hello everyone, this video is mainly for analyzing the flight dynamic of the Albatross UAV. And as it could be seen here, the first step would be to do the weight balance. Then if we go to the center of gravity CG, we can change the location of CG here, Z direction. If I enter 0.01, it should shift the CG backward. And if we place the CG at 0.13 meters, the aircraft loses its balance, so the maximum will be 0.13. The reading of 6 CG positions are measured and plotted in Excel. To be seen here, the reading of nose gear, Portman gear, and starboard gear are placed here. The moment arms are fixed, assumed to be fixed. They are the distance between the gear and the CG. Movement could be calculated by multiplying the moment arm and weight, and then CG precision could be calculated using the total weight and total movement by summing them up. The estimated CG is approximately proportional to the actual CG. You could see there is a little bit error here, but it doesn't do a huge difference. Could be approximated. As it could be seen here, it's the graph of thrust versus RPM. Although it's not very uniform, but in general the thrust is proportional to RPM. The third part will be the static control response. And if we enter the student ID here, we get an aircraft which is not well functioned. Some of the control systems might be inversed. For example, here the elevator, aileron, and the flaps are inversed. And then here we can adjust them. For example, if we deselect the aileron and then we give it a positive roll, you can see that the starboard wing generates lift and it rolls in the opposite way, which is not what we want. And it's the same for the flap and elevator. To investigate the relationship between the thrust line and the CG, and then we can adjust the CG here. We set it as 0, and then press Ctrl G. Now we got the 4 parameters: roll, yaw, angle of attack, and elevator input. The angle of attack is relatively negative, which means it has a nose down pitching moment, showing that the CG is far too forward. And we adjust the CG position to 0.01 meters after the leading edge of the wing. And here shows the CG as percentage of the mean aerodynamic core. So here is 4.29% of the mean aerodynamic core. Here we can see that the angle of attack increases as we adjusted the CG position. By the way, here the angle of attack is kind of blocked by the yaw, so we disable it, then we can see the angle of attack line. Now we can play with the aircraft as we adjust the elevator, which gives a nose up pitching moment. It also affects the yaw a little bit. And if we are going to roll the aircraft, worth noticing, as the wind speed increases, it responds faster and it becomes more sensitive. And the roll angle is shown here in degree. Here we investigate the relationship between the thrust line and the CG. We need to adjust the CG so that when there is a change in thrust, the aircraft doesn't generate an additional pitching moment. We can see that the angle of attack increases as we turn on the engine. Then the y-axis is set as minus 0.03. Now if we turn on the engine, the angle of attack doesn't change, showing that the CG lies on the thrust line and no pitching moment is generated. Nice. For the flight performance, we use the wind tunnel. Could be seen here when we run the simulation. A series of data are generated. Here is the parameter to be changed. For example, the flight deflections and the CG positions. The data will be plotted in Excel. In the red column is the lift coefficient versus the angle of attack. X-axis is the angle of attack and y-axis is the lift coefficient. The maximum lift coefficient occurs at the angle of attack of approximately 10 degrees, 9 degrees or 10 degrees. And for the graph of drag coefficient versus the lift coefficient is plotted inversely, but should be okay. And then it's the lift over drag, which is the glide ratio. Graph shows the glide ratio over lift coefficient. So it seems that the highest glide ratio appears at the lift coefficient of 0.5. We've seen that is approximately 13. It's a reasonable glide ratio. And then it comes to the longitudinal trim. This is a graph of moment coefficient, CG, versus the lift coefficient. So it can be seen here, different from the example, the CG increases as the lift coefficient increases. The reason could be that center of gravity lies behind the aerodynamic center, which means when the lift is generated, the aircraft has a nose of pitching moment. And for the picture of moment coefficient versus the lift coefficient, four CG positions are measured, and then from this picture it could be seen the steady point is approximately above 0. Let's say 0.05, 0.09. Now we are in the part of free flight. For ground handling, there could be possible failure modes due to excessive steering input during the high-speed ground testing. This might cause the aircraft drift and then crash during testing. To avoid this, less steering inputs could be given to the aircraft. The minimum unstick speed, which is the minimum speed the aircraft requires to take off, measured here is approximately 19 meters per second. It is a bit higher than the stall speed measured, which is 70 meters per second. Moving to the cruise trim, and to find out the elevator and the RPM required to achieve the static speed, which is 20 meters per second. The thrust required is 11.1, rotating at 37 RPM, and the elevator trim angle is minus 9.1 degree. And also, the aircraft is experiencing a fuel going. The minimum trim flight speed, meaning the minimum speed for maintaining steady level flight, is 17 meters per second, here mentioned before. And the maximum trim level flight speed is 50 meters per second. As it fluctuates between 48 and 52, the average is taken to be 50. To estimate the long period natural frequency of the aircraft, or say the fuel going, the graph of angle of attack versus time is plotted. As you can be seen, in the middle is a steady flight. The data points are in a shape similar to a sine wave. The wave peaks are picked to calculate the delta t, and then the frequency could be calculated. Finally, enjoy the steady flight.